Okay, continuing with definite integration, we're now going to evaluate some definite integrals using the fundamental theorem of calculus. So what the fundamental theorem of calculus says, for a continuous function where we're on an interval from a to b, we can calculate the definite integral from a to b. So notice that my limits of integration here are the endpoints of that closed interval. My integrand is the function, and what we're going to do is integrate using our rules of integration that we've had, but then where the fundamental theorem of calculus kicks in is how we evaluate it on that interval from a to b. So what you're going to do once you have done the integration is plug in the upper limit of integration, plug in the lower limit of integration, and calculate the difference between those. So let's take a look at an example. So in this first one, kept the function very simple. We just want to calculate the integral from -1 to 2 of the function x to the 4th. So the first thing that we're going to do is just integrate using our rules of integration. So remember, the rule of integration says we take the coefficient over the exponent plus 1. And then my new exponent is the exponent plus 1. Now, the first difference that you're going to see when we do definite integration is we're not going to add in that constant. We want to evaluate this integral from -1 to 2. So because of, in that fundamental theorem of calculus, because of that subtraction that we have here, if you put in the plus c, those c's would end up subtracting out anyway when you do the evaluation. So we're not going to put in the constant of integration, but what we want to do is indicate that we're going to evaluate this integral from -1 to 2. So notation-wise, you put a straight line segment here, and you put the limits of integration on that line segment. So what this indicates to anybody looking at it is this is the integral of x to the 4th, and now we want to evaluate it with these limits of integration. So those should be there on this step. So now what we're going to do is apply that fundamental theorem of calculus, which says that we first plug in the upper limit of integration. So in for x, we're going to replace that x with 2. So we've got 2 to the 5th power. And then we want to subtract from that what we get when we plug in the lower limit of integration, which is -1. So I've got 1/5, and then my -1 to the 5th power. So remember, it's always subtraction in between them, and it's always the upper limit first, lower limit second. So now we just want to do the calculation. So 2 to the 5th power is equal to 32, so we've got 32/5, and then -1 to the 5th power is -1, so -1 times -1/5 would make that a +1/5, so our value for that integral is equal to 33/5. Okay, let's take a look at a second example. So in this example, we have the integral from -1 to 1 of 4 minus x cubed dx. So again, the first thing that we want to do is just integrate using our rules of integration. So for a constant 4, the integral of 4 would just be 4x. And then for x cubed, I've got coefficient over exponent plus 1, exponent plus 1. And then that new notation that we want to integrate that from -1 to 1, or I'm sorry, we want to evaluate that from -1 to 1. And now we're going to put in our fundamental theorem of calculus by evaluating that at the upper limit, which would give me 4 times 1 minus 1/4, 1 to the 4th power. And I'm going to put brackets around that because that's just plugging in that upper limit of integration, minus Now I want to put in the lower limit of integration. So I'm going to have 4 times -1 minus 1/4 -1 to the 4th power. So the brackets are just showing the two different limits of integration and making sure that I don't make any mistake with my signs. So let's do the evaluation. 4 times 1 is 4, and 1/4 times 1 to the 4th is going to be 1/4, so this is 4 minus 1/4 in that bracket. And in my other bracket, I've got -4, and then -1 to the 4th power is going to be positive, so that's going to be minus 1/4. So 4 minus 1/4 is equal to 15/4, and -4 minus 1/4 would be -17/4. And then, of course, minus a minus here makes that positive, so if I add that together, I get 32/4, which is equal to 8. So there's my value for that definite integral. Okay, let's take a look at one more example. And if you want to shut the video off and try this yourself first, and then come back and see if you got it right. So we're going to start by integrating each one of these terms in my integral. So I'm going to have coefficient over exponent plus 1, exponent plus 1, minus coefficient over exponent plus 1, plus, to integrate 3, we attach an x. And I want to evaluate that from 1 to 2. Now I can clean up this middle term here. I'm going to cheat a little bit and just put that as minus 4x squared. It's the only one where the coefficient needed to be simplified. Okay, so we start now by first plugging in the upper limit of integration. So everywhere I see an x, I'm going to replace it with 2. So I'm going to have the 4 there, 2 squared, plus 3 times 2. And then we want to subtract from that what we get when we plug in the lower limit of integration. Now that lower limit of integration is just 1, so you probably wouldn't have to write out the 1 for each one of those substitutions, but I'm going to do it just for the sake of you seeing where I'm getting my values from. Okay, so if we do this arithmetic, let's see, 2 to the 5th power is 32, times 3 would be 96 over 5, minus 2 squared is 4, so that's 16 plus 6. And over here, the nice thing about that, those are all 1s, so this is just going to be 3/5 minus 4 plus. So what I get when I do that computation, when I do 96/5 minus 16 plus 6, I end up getting 46 over 5. And then minus 3/5 minus 4 plus 3 is -2/5. So the minus minus becomes plus, so I end up with 48 over 5 for my overall value. So it's just the same properties, rules of integration that we had. Now you're just adding in, evaluating that integral for the difference of the two limits of integration. Okay, so one application to this is finding area, so talking about the integral as area under the curve, which we introduced in the last video. So in these problems, the only difference is you're setting up the integral to begin with. So in this example, we want to find the area under the graph of that function y equal 2x cubed plus 4x, and we want that closed interval from 0 to 3. So the first thing to do is to actually write out what your integral would look like. So my integral symbol and my limits of integration are going to be the endpoints of that closed interval, so 0 to 3. And then my function is 2x cubed plus 4x, and we want to integrate that with respect to x, so I have my dx. And now it just becomes a problem similar to what we were just working on. We start by doing the integration. So coefficient over exponent plus 1, repeat that, coefficient over exponent plus 1, and then we want to evaluate that from 0 to 2. Now I'm going to clean this up a little bit as I plug in my upper limit of integration. So my coefficient here is 1/2, and I'm going to replace the x with 2, plus here my coefficient simplifies to just 2, and then plug in my 2 for x. And then I want to subtract from that what I get when I plug in 0. Now every one of these terms here has a 0, so has an x, so both of those terms are just going to turn into 0. So I'm not really subtracting any value that's going to affect what I get when I calculate that. So when I do that arithmetic, I end up with, let's see here, 2 to the 4th power is 16, so I get 16 over 2, plus 2 squared is 4, so that's 8, and 16 over 2 is 8. 8 plus 8 gives me an area under the curve of 16. Okay, so pause the video. Here's another area under the curve problem. Try that, see how you do. So we start by writing our integral. So my integral will go from -1 to 2, since that's what my endpoints of my interval are. And my function x minus 3x squared becomes my integrand. And we use our rules of integration to evaluate that. So my coefficient over exponent plus 1 minus coefficient over exponent plus 1. And we want to evaluate that from -1 to 2. So start by plugging in the 2. So we're going to have 1/2 times 2 squared minus, this coefficient is just 1, so I'm just going to have 2 to the 3rd power, minus, now plug in your lower limit of integration, so 1/2 times -1 squared minus -1 cubed. And doing that arithmetic, 1/2 of 4 is 2, 2 cubed is 8, minus -1 squared is +1, so 1/2. -1 cubed is negative, and then the negative in front of that is going to make that +1. So we end up with 2 minus 8 is -6 minus 3/2, which is going to give me -15/2 for my overall. So what that overall negative area would indicate would be that you have more of the curve underneath the x-axis than above the x-axis, if not that entire region being underneath the x-axis. Okay, for number 6, it's just another quick example of the same idea. So again, if you want to try it yourself first and then come back and see how you did. So we first create the integral, and our integral would be from 1 to 4 of 3x minus 2 dx. And so if we integrate first, we're going to get coefficient over exponent plus 1 minus, for the integral of 2, we attach the variable x, and we want to evaluate that from 1 to 4. So we start by replacing all of those x's with 4, minus, replace all of those x's with 1, which is just going to give me 3/2 minus 2. So on the left-hand side here, 16 times 3/2 would be 48/2, or 24, minus 8. And over here, 3/2 minus 2 would be -1/2. So we've got 24 minus 8 is 16 plus 1/2 would give me an overall area of 33/2. So you've seen now all of the properties of integration that we're going to cover. All of the areas that we were computing in these problems were the area under the curve to the x-axis. So in the next section, what we're going to do is use integration to help us calculate the area between two curves. But you've got all of the properties that you'll need for that. So it's just a matter of practicing your integration techniques and then adding in that with that this new idea of calculating that integral using your upper and lower limits. If you have any questions on this video or if you have any questions on your homework, make sure that you email me.